Welcome to iLecture-Online. You will find that the Maclaurin series sometimes give you a handy way to do something that otherwise would be quite difficult to do. For example, the integral of e to the minus x squared dx. This is how you can approach it. We know that e to the x can be written as the infinite sum from n equals 0 to infinity of x to the n divided by n factorial, which means that this is equal to 1 plus x squared over 2 plus x cubed over 3 plus and so forth. Now, can we draw a relationship between this and this? You can see, well, here you have e to the x, here you have e to the minus x squared. So if we take every x and replace it by a minus x squared, and then we plug that into our infinite series, now we have an infinite series that represents e to the minus x squared. So e to the minus x squared can be written as 1 plus, instead of x, we write minus x squared. Instead of the x squared, we write minus x squared. We have to square that, divided by, and of course, it would help if I add the factorials in the denominator. 2 factorial plus, this would be minus x squared to the third power, divided by 3 factorial, and so forth. Now let's clean it up a little bit. This is equal to 1, and here we have minus x squared. Here we have plus x to the fourth over 2 factorial, and here we have plus x to, let's see here, that would be, nope, not plus, that's going to be minus, because we have minus 1 cubed, so minus x to the 6th over 3 factorial, and that would be plus x to the 8th over 4 factorial, and I think we can see the pattern now. So if this is equal to e to the minus x squared, then if we want to integrate e to the minus x squared, that's the same as integrating this infinite sum. And so that means that the integral of e to the minus x squared dx is equal to the integral of, and we have 1 minus x squared dx. So let's go ahead and integrate that and see what we end up with. So coming over here, we can now say that the integral of e to the minus x squared is equal to the integral over here. That means the integral of 1 is x plus, or minus, we have minus x cubed over 3. And then here we get plus x to the 5th over 5 times 2 factorial. And then we have minus x to the 7th over 7 times 3 factorial. And then plus x to the 9th over 9 times 4 factorial. And you can see the pattern now. Of course, you also have a constant of integration. By the way, we should put in a dx to make it complete. Now, we're going to evaluate that integral from x equals 0 to x equals 1. So that means the integral from 0 to 1 of e to the minus x squared dx is equal to evaluating this whole sum from 0 to 1. So we get x minus x cubed. We can't forget the constant of integration from 0 to 1. Now, of course, the constant of integration will disappear when we plug in the limits, because first we'll plug in the upper limit, and then we plug in the lower limit, we subtract, the c will drop out. But notice also that when we plug in the lower limit, every one of the other terms will go to 0, and that means what we have left is just the upper limit. That would be 1 minus 1 over 3 plus 1 over, that would be 10 minus 1 over, that's 6 times 7, which is 42, plus 1 over, that's 24 times 9, which is 240 minus 24, or 216, and on like that. So the integral from 0 to 1 of e to the minus x squared dx evaluated will simply be the infinite sum as follows. So notice, using Maclaurin series, we can take an integral that otherwise would be very difficult to execute and do it rather simply by finding the approximate equivalent to a Maclaurin series we're familiar with, then making it look exactly the same by making the proper substitution, and then the rest of it is fairly straightforward. And that's how it's done.